8.2 is on what we call digraphs, which is short for directed graph, or more simply, it's just a graph with arrows. So in the past few chapters, we've been working on, say, for example, street routing problems where we build graphs to represent, say, a neighborhood where the dots were the intersections and the lines were the streets. Or in chapter 6, we were dealing with traveling problems where the dots could represent locations that we wanted to go to, and the lines represented the cost that it took to get to that point, whether it be in miles or dollars or time. Um, so in with digraphs would just be a graph where each line or each edge which connects the vertices together has an associated direction where that is the only way to go. So say for example in a street sweeping problem like from chapter 5, like I mentioned this at the time, but there is a possibility of one-way streets happening. And if we're trying to do a street routing problem, we can't necessarily go either direction on the street that's available to us. And if we wanted to add that layer of intricacy to those problems, we could use an arrow to designate, okay, you can really only go this way in those problems. But in those problems, we assumed that all streets were two-way streets. And in chapter 6, we assume that from traveling A to B and B to A, it would be the same either way. But as I mentioned at the time as well, sometimes it would cost more to fly from A to B than it would be from B to A. So the set of costs would not necessarily be the same as we assumed in chapter 6. But you could still use digraphs in those chapters. It would make the problems a little bit more complicated, but still solvable, using a lot of the same theory. But sometimes there would be different theory we need to develop for those more difficult types. Anyways, in chapter 8, which is on task processor problems, we use digraphs to represent what the precedence relation. Basically, when looking at a graph with arrows on it, or a digraph, each dot would represent the tasks in those problems, and each arrow would represent what order would need to happen. So, like how I'd read this graph is task A. After task A, I could do either task D or task E, and B. Since there's an arrow going from B to D, what that's implying is that D can't be worked on until B has been finished. But it's a graphical way of representing the tasks at hand. And we'll return back to our automotive tech example and build a digraph that makes sense to represent that in a minute. But some terms related to digraphs, and basically each of the things is just called something different in this chapter, but it's all kind of the same idea. Each of the edges are called arcs. So we'd say the arc from A to D, just it's a specific term to an arrow rather than a direct line. We could say the arc set or the arc list is just a list of all the arcs. So in this graph, we'd have AD, AE, BD, BE. It would always be listed in its order. It wouldn't be listed as EB because that would imply it's the other arrow, the other reverse arc, which would be unique. A path is formulated from a set of adjacent arcs. So like B to E, E to G, G to I would be one example of a path. Arcs that are connected to the same vertex are called adjacent. So EG and GI are adjacent arcs. A cycle is the same as a circuit. Cycles are not very common for a task processor problem, because it would imply that there's a set of arrows which would come back to the start. Like let's say, for example, I came all the way back and had an arrow pointed to A. That would form a circuit like that. But for precedence relations, it doesn't make any sense to do that. But in what we often, in a common sense, people often refer to these as flowcharts, just a set of things that happen. Like for example, you're trying to build your schedule and you want to know what classes you need to take in which semester. This could represent math 100. This could be math 200, and obviously you don't want to take that class until you take that class. You're going to be up the creek. But sometimes in flowcharts you have a cycle, and a lot of times in algorithmic design you want something to repeat, and that can happen in a lot of contexts, but not in this chapter. And also in degree and out degree, it just refers to, we have the term degree to refer to the number of edges connected to the dots. Like vertex A has 2 lines, so that's at degree 2. But basically, if we wanted to differentiate between how many are coming in and out, that is a different kind of concept. Like, for example, vertex E has an in degree of 3 because it has 3 guys coming into it, and has out degree of 2, but its net degree would still be 5 in the traditional sense of the term. And all that means, if we're trying to extract the meaning, the meaning of in degree and out degree, is in terms of tasks. Before I work on E, I need to do A, B, and C. So thinking about its in degree, that just means it has 3 things that directly need to happen before it in order for this to work. And out degree meaning 2 means there's 2 things that are waiting for it to finish before we can work on the next tasks from there. So let's return back to the prior example, the automotive tech problem, and we'll try to draw a digraph for it. Basically going to make a series of dots and arrows to represent the necessary order in order to get our car repaired. So let me go back to the previous slide because I want to pull up that problem, and we will build it on, I'll use my whiteboard. But if you're looking at the packet, it should be, this question is number 1. And we often refer to these as a project digraph or precedence graph or precedence digraph. But digraph just means it's got the arrows, and then precedence just means this graph represents a series of tasks which have one task takes precedence to another as well. Or, project digraph just meaning it's for the whole series of tasks, and we're trying to develop a digraph for the whole project. But in this example, we had 5 tasks to get done. So that would mean we have 5 vertices on our digraph, A, B, C, D, E. We could just graph them randomly, but usually we try to have them flow from left to right. I think that's going the reverse way, as you can see it. So left to right, it's backwards. But yeah, left to right, because that's usually how we read, but it doesn't have to be left to right. Some flowcharts go bottom to top, top to bottom. It doesn't really matter as long as it makes sense. So, anyways, my point was we're going to have 5 dots, and also how we're going to determine where the arrows go is based on the necessary restrictions on the order. So in that problem, the text couldn't begin any work until they had the parts. So meaning task A, this had to happen first. So if we're building it from left to right, we want to put A first on the left-hand side, and then the other tasks are going to stem from A. And the painting and exterior finish could not be done until the bodywork has been done. So basically, B had to be finished before D could be started. So basically, that's just going to mean B is going to have an arrow going into D, and that's all the information we know. So basically, what I'm thinking or how I would get started is I'm going to put task A first. And when we're building the graph, we always label them with a vertex as we normally do in graph theory, just so we can specify what each thing means. And it's important to remember that each dot means a particular thing. Often we might refer to vertex A, we might call it like parts or something. You don't have to name it. You could label it P. That way, it's a little bit easier to remember what that is. But like in this case, we usually arbitrarily use letters in alphabetical order to assign to the task randomly. But you could pick sensible choices so that another person, if they were looking at your graph, could understand it. But basically, A had to happen first, so I'm going to put that on the left. Then I have B, C, D, and E that come from A. So B could happen directly after A, but another part of the precedence relation was that task D had to wait for B to finish because we could not do the painting until the bodywork had been done. And that was kind of the second part of that sentence. Painting exterior finish could not be done until the bodywork has been done. And then otherwise, the engine and transmission, those did not have to wait on the bodywork or the painting. It didn't make sense. So basically, C could happen directly after. But I did need to wait to get the parts still. I couldn't fix the engine without the correct parts. And same with the transmission. Those did not have anything to do with the bodywork, and the painting could be done independently of those. But all of them had to wait on getting the parts. And one other thing that we often, so the digraph is almost completed, but typically what we also put on the digraph is the processing times for each of the tasks, because I can kind of see what order things need to get done, but it also helps to know how long each task takes when we're working to build a schedule. So in this case, it took 3, 4, 5, 7, and 3 hours. And how we usually do that is by putting parentheses next to the vertex. I already forgot the numbers. 3, 4, 5, 7, and 3. And that's another way I can kind of imagine, well, how long is it going to take to do those tasks? And technically, it's not a necessity. Additionally, you do not notice that it's a little different than the graphs from chapter 6, because on those graphs we put the numbers on the lines, because it was like the lines meant like a cost of traveling between the 2 points. Here, each of the dots is what is what is weighted, because it's really the tasks that take time, not the arrows themselves. And notice that there's not enough arrows to represent all the tasks, so it wouldn't make sense to put the numbers on the arrows. You actually could develop that, but it's not necessary. And one other thing that the book does, but I generally don't do, but I wanted to show you this because if you go and look at the examples in the book, it can be really confusing, and not maybe not that confusing, but it's a little bit different. But they always have a start and an ending vertex on their graphs. So basically, like on the left-hand side, and what this kind of indicates is, and this is kind of important for computer algorithms, like what is the beginning of the project, what indicates the start and the finish? Because in general, it might not always be obvious where do you begin, but that usually it's from left to right, so it is obvious in these problems. And usually start is met with a 0 because it doesn't really take any time. This is just like we're beginning this, we're starting it. And for a computer, it's kind of like it needs a starting point for in terms of thinking. It doesn't actually take time to start. And also another thing to note is, well, when does this end? Another thing that does not take time, but it's a point that we can kind of say explicitly, well, once I've done all the tasks A, B, C, D, and E, then we're done. And so all of the final vertices would link into the end. And this is typically how the digraphs will look in your textbook, but you don't need to do that. That's optional in my opinion. But I thought I'd just mention that so it's not confusing. And I'm going to leave those out on all my examples in the future. Anyways, this would be it. We're now done with our project digraph, and it helps to see. I think it's very helpful in visualizing the order of the tasks, and I can get a better understanding of what my project's going to take from here. And later we'll talk about actually scheduling it and finding out the best way of getting them done, but that's to come next week. So additionally, okay, there's another fresh example. Let's just do one more. And in this case, you can pause the video and try it for yourself if you'd like. But in this example, it says to create a precedence digraph to describe the following sets of tasks. So if we take a second to examine these tasks, this project would be a kitchen repair. Say for example, you own a company that replaces kitchens and fixes things within a kitchen. And you fix kitchens all the time, and you know pretty much the average amount of time it's going to take to do everything. Like for example, you need to remove the appliances, remove the old flooring, remove the cabinetry, blah blah blah, and all this stuff takes time. And my parents are working on their kitchen because they had a water leak right now, and now that I'm looking at these numbers, this is vastly unrealistic, but just pretend that this makes sense. But obviously everything, these are just examples that I made up or that someone else made up. And you could, to simulate realism, but these numbers probably should be a lot higher. And also, what about getting the parts? Those are other factors that if you actually own a business and we're trying to do this, you would have to take everything into account. You have to figure this out yourself. Regardless, let's try to build a precedence digraph for this. So notice that any task which has no prerequisites, that's always going to happen first. And what I would usually do is assign letters to each of these. Like I could call this RA, RF, RC. But I'm just going to call them A, B, C, D, E, F, G, H, I, J in that order, just for the sake of simplicity. And actually, let me pull this up over here so that I can see it while I'm working on my whiteboard. And let's go ahead and work on it. So removing up the appliances is going to come first. That's going to be task A. Actually, I'll do that as RA because I haven't labeled them. And you can choose whatever you want, however you want to label your vertices. So RA is going to be first, and that took 1 hour. And then next up, and notice that I created this table to flow in a sensible order, but the task wouldn't necessarily be written this way. A lot of times it might be a sentence that you have to read and kind of use your reading comprehension, which is not everybody's strong suit. Like when I was younger, I had a very difficult time with like reading a sentence and extracting the important information from it. Even though I was really good at the abstract math side of problems, it took me a lot longer to be able to understand word problems as well as I do today. But anyways, okay, yeah. So removing the flooring and removing the cabinetry could happen after I remove the appliances, and that makes sense because you can't take out the cabinets when the stove is still there or whatever. So removing the flooring, which is going to take 2 hours. Again, that is probably not very realistic. Maybe it's a really, really small kitchen. And then removing the appliances, removing the cabinetry, which is going to take 1 hour. Then after, to install the flooring, we had to first remove the flooring, obviously, and the cabinetry. So that was going to happen directly after those two tasks. So next up, after those two are completed, we can then work on installing the flooring. Going to take 4 hours. Then to install the cabinetry, prerequisite was the flooring. So after the flooring, we could then do the cabinetry, which took 3 hours. Once the cabinetry was installed, we could do the backsplash, the paint, and the countertop. So backsplash, paint, and the countertop. I'm going to have to use something different than IC because I already use it, but ICT, I guess, for countertop. And we'll do cabinetry to ICB. And the graph is already getting pretty hectic, but that's just because in a more realistic project, you might have 5, 10, 25 tasks. And, it just depends on the scope of your project. Then the sink had to wait for the countertop. That makes sense. Installing the sink, which took 1 hour. And same with the appliances, which took 30 minutes. Also with the units, obviously I don't want to put 30 there because we want to make sure the times are the same for everything. So I'm going to use just 0.5 for a half hour. And it's not exactly perfect. It's a little bit ugly, but it'll get the job done for later, for when we actually work on scheduling these things next.